Let's look at the electric field. Now, if we take a charge, just a plus charge, and I put it there, that charge will have a field pushing away. The reason it's pushing away, we're saying what will happen if you bring in a positive charge to the neighborhood of this one. So if I have in my hand a positive charge and I bring it in, what is this charge going to do to that charge in my hand? It's going to push it away. That's why it's pushing for a plus charge. For a negative charge, if this is negative, and if I bring in a plus charge slowly to that one, what is this charge going to be doing to my negative plus charge here? It's going to pull on it. So again, what is the effect on bringing a plus charge to that area? If this charge is negative, that's positive. We know they attract each other, they pull on each other. That's why the force will be pulling in that direction. If I bring in a positive charge to this plus charge going to go away from me. So it's pushing away on it. And the way we calculate the electric field is going to be K times the absolute value of this charge that you have sitting here divided by R squared. It is very similar to the force. Remember what the equation for the force is? The force was what? K times what? Q1 times Q2. So it's missing Q2. So if you look at this, the electric field is really the force, whatever this equation, if you divide it by Q2. Or you can say the force equals Q2 times the electric field. And force is a vector, so the direction of it is going to be the same direction as that electric field on Q2. Now let's take a couple examples, go through them and see what will happen here. Just like forces, and I'll do actually two of them here instead of just one. Let's pick a charge here, positive or negative. Somebody chooses one and give me a value for it.
Negative 2.2.
Okay, let's put negative 2.2 here, Tyler. And let's put one down here. Somebody pick a value and a charge of it.
Negative 3.1.
Negative 3.1, Alex, microcoulomb. And let's say I want to find the electric field here. So there's no charge here, but if I do bring in a charge there, is going to be, that charge will be affected by whatever the electric field. So what is the value of the electric field at this point? So keep in mind, there is no charge here. So let's get a distance here. Let's say this distance is, well, I'll just give you that distance from, well, I'll do this. This is 4 or 0.4 meters. This is 0.2 meters. So you gotta do extra work there. Excuse me. Now we said when you have a negative charge, it's going to have electric field pulling toward that charge. So the electric field here is going to be pulling toward the charge, is going toward the negative charge, is going away from the positive charge. So this will be going that direction, this will be going in this direction. And I need to know what the net result of that electric field. Let's call this charge Q1. Let's call this charge Q2. So this is electric field 1 due to charge 1. This electric field due to charge 2. We'll get the angle later. I need to know what the distance from here to there. Notice that distance is not given to me. Let's call that R. R squared is going to be what? 0.4 squared plus 0.2 squared. What is 0.4 squared plus 0.2 squared? This is 0.2. Could be. What's 0.4 squared? 0.16. What's 0.2 squared? Yep, it is 0.2. R squared equals 0.2. R equals what? The square root of 0.2. Which is 0.447. Let's find the first electric field, E1. It's K times absolute value of Q1 over R squared. 9.0 times 10 to the 9 times Q1, which is 2.2 micro, over R squared, and R happens to be 0.447. And I came up with, notice electric field has a large value, 99,000. What do you think the units for it? Newton per coulomb. If you put a coulomb charge here, that force will be 99,000 Newton. Coulomb charge is massive. You're not going to have a coulomb. So usually the charge is in micro, so that number becomes really small. But if you end up with 1 coulomb of a charge right here, that force will be 99,000 Newton. I hate that throat. What's E2? K times the absolute value of Q2 over R squared. Q2, and what is Q2? That's 3.1 micro. I got 139,500 Newton per coulomb. And now I got to find what the result of that electric field. Remember, that's a force. You need to know all the angles here. You're going to put your x-axis right here and your y-axis. So this is my y-axis. This is my x-axis. And I need to know what these angles are. This is the y-axis, x-axis. Can you tell me what that angle is and what this angle is? I need to know. I can find that angle if I call it, I don't know, beta. That angle. Tangent beta, I don't want to give you that number because I want you to use trig here, is the side that's opposite over the adjacent. What is the opposite? 0.2, what's the adjacent? 0.4. So tangent beta equals 1/2. Beta will have to be what? Inverse tangent. 26.6 degree. So now I know what that angle is. 26.6 degree. Now let's redraw that on a bigger scale. X and Y axes right here. Here's one force or one electric field in this direction. One in that direction. The one coming down here, that's, which one is that? E2. That's 139,500. The one going up is 99,000. We know this angle is 26.6 degrees. We know this angle is 26.6 degrees. And find the result of these two vectors. Let's look and see. Break them down, 3 parts. Vector, x component, y component. What's the first vector here? Let's say this is the first vector. What's the value of that? 99,000? And what's the angle?
26.
Try again. What'd you say?
26.6.
Try again, Tyler.
Which angle are we looking at?
You always want to measure the angle from one place. Reference. Your reference always has to be this line when you measure the angle. Otherwise, your pluses and minuses is not going to match.
153.4.
153, Michael? 153.4, which is 90 or 180 minus 26.6. Yep. So the x value will be 99,000 cosine 153.4, and the y value is 99,000 sine 153.4. And I got a negative value for this, which should be negative. It's to the left, 88,521. The y value is going to be 44,328. Now the second vector, what's the value of that? 139,500. And what's the angle? Yep, 206.6. So the cosine will be 139,500 cosine 206.6, and the y value is going to be 139,500 sine 206.6. Negative 124,735. And the y value is going to be 139,500 sine 206.6. Negative 62462. Let's take the result now in the x and the y. In the x direction is going to be 88,521. Add to it 124,735. Negative 213,256. The result in the y direction, 44,328 minus 62462. It's negative 18,134. Again, which quadrant are we in? It looks like we're in quadrant 3 now. We get a negative in the x direction. We get a negative in the y direction. So the result is going to be right here. And when you're in the third or the second quadrant, when you get your angle, you better add to it 180 degrees. Because the calculator always gives you the wrong answer. So r is going to be the square root of r sub x squared plus r sub y squared. So let's take these two numbers, square them, then take the square root. 213,256 squared plus 18,134 squared. Take the square root of that number. I came up with 214,026. Again, this is Newton per Coulomb. And theta, it's electric field, it's the inverse tangent of y over x, and don't forget to add the 180 degrees because you're in this quadrant. If you're in 2 or 3, you always add the 180 degrees to your answer. Y, which is negative 18134. X is 213,256 with the minus. Second tangent, 18134 divided by 213,256. Plus the 180. I got one net result of 185 roughly. That's the value of it, and that's the direction of it. And if you get 3, 4, 5, 10 of them, the process does not change. Let's take another example here. And that's really capacitors. You see that in electronic devices all the time. If you ever open an electronic device, sometimes you see a little blob that looks like this. Usually green color or light brown color there. And what that is actually, two plates on top of each other, like this. And there's a wire coming this way, and there's a wire coming that way. We put a charge between them. So you attach them to plus or minus here. So what happens is you take the top plate and you make it a positive. And you take the bottom plate and you make it a negative. And by doing that, you create an electric field between them. Remember, when you have a plus charge, the plus charge does what to the field? It pushes away from the field. So it's pushing down here. It's also pushing up there, but we don't care about the up. It's pushing all the direction. And what about the negative charge? What does the negative charge do? The negative charge has a field pushing toward that. So this will have a field pulling toward that. I'm only interested between the two plates. Between the two plates, what I see is this is the plus charge here, and this is the minus charge. And I have a field going this way, from the plus to the minus. That's what we have. If my plates were standing up like this, the field would be going that direction. Always from the plus to the minus. So two plates, two metal conductors, two plates, space between them. The space could be filled with air, could be filled with water, could be filled with rubber, anything to change the value of that capacitor creates what we call a capacitor. And now we have electric field here. We use this a lot, by the way. We use that on laser jet printers. When you and I go to print, what happens actually, we take that ink drop there, which is this drop, and we put a charge on it. And we fire, because if this is not charged and you shoot this, it will go straight. Well, it won't go straight because the gravity is going to pull on it, you know. But at high speed, let's assume it goes straight, but it's going to start to dip down. If you charge this with a plus charge, what's going to happen is going to go like this. Why? Because this is pushing down on it. If you charge it with the negative charge, it's going to go like this. It's going to make it go higher. So when you're printing, actually, what you're doing, you're charging with the laser jet printers here, or the inkjet printers, not the inkjet printers. We charge these ink drop and we shoot them toward the paper, and we can make it print high and low based on that value there. Then we have at this end, we have a collector that collects all these ink drop that didn't stick, left there, didn't touch the paper, didn't make it. We collect them, take the charge away from them, put them back in it, and reuse them. So let's see what's going on there. Let's take an example on that. So now we have a capacitor. We have a plate that looks like this. And positive plate, we have a negative plate. Now I have an object with me, has a mass. And I take the object and I put it here. The mass of the object is 0.0250 kilogram. And I decide, you know what, I'm going to charge that with a negative charge. Q for this is negative 3.1 micron. 3.1, if you can see the point, that's a point there. But I have that charge attached to a string, because if it's not attached to a string, guess what will happen? Boop, this will suck it in, and it will stick to the wall of this. But it has it attached to a string, so initially this was hanging straight down. Once you put it into the field here, it's going to look like this. It was attached right there to a string. But because this is negatively charged, this plate is going to pull on it, this is going to push away on it. The question here, if this angle between them, where it was horizontal straight down, was vertical, if this angle right there, theta, is equal to 10 degrees. I just use 10 degrees. Can you tell me what the tension of the thread is? And can you tell me what the magnetic field, what E is? There's a magnetic field because the plate's here. I just don't know what that field is. So there's a field here. It looks like this. And now let me take this charge and analyze it. Here's my string, was straight down initially. The ball was right here. By putting the field there, by adding the field, it made it go in that direction. The field is pulling on this. Why? Because that's a negative charge. If it was plus, it would be pushing away. It's pulling on it in this direction. There's a force of pulling. And we know the force equals to that charge times the electric field. And since that charge is negative, with the value of that, we know it's 3.2, I know the direction, or 3.1 micro, times the electric field. And I know it's pulling in this direction. So I can just throw it pointing to the left, but the value of that is this. I also know that there's a force pushing down. That's the weight of that object, which is mass times gravity. That didn't change. We know what the mass is. So that's 0.245. And I know there's the tension in that direction. And if this is 10 degrees, if you make a triangle here, guess what that angle is? If that's 10 degrees here, then what is this angle? What is it? 80, Jonathan, yep. 80 degrees. And now the thing is now moving. Why isn't it moving? Because we have a static equilibrium. And if you have equilibrium, that means the net force in the x direction has to be 0, and the net force in the y direction has to be 0. That's why it's now moving. Another way of saying it, the forces, if you take all the forces pointing to the right, they have to equal all the forces pointing to the left. If you take all the forces pointing upward, they have to equal all the forces pointing down. Let me take this actually and break it down a little bit there more. So these are my forces. I got 3.1 micro times e to the left. I got 1 down, which is 0.245. Now I'm going to take that tension, break it down to x and y component. I'm going to break it down to this direction, which is what? T cosine 80. And it's going to have a value going upward, and what's the value of that force? T sine of 80. Let's come back, look at this. All the forces to the right equals all the forces to the left. What do we have to the right? T cosine of 80. What do we have pointing to the left? 3.1 micro times E. How many unknowns in this equation? Do you know what E is? Do you know what T is? Two unknowns. Let's look at this one. Up equals down. What do we have pointing up? T sine of 80. What do we have pointing down? How many unknowns in that equation? Only one. Can we find what T is? T equals 0.245 divided by sine of 80 degrees. 0.249. If I know T, can I find the electric field? Go back to that one. 0.249 cosine of 80 equals 3.1 micro times E. E equals, let's see, $13,936. Again, Newton per Coulomb. If you take a 1 Coulomb charge and hang it right there, that's how much that force will be. Now, if this charge was positive, instead of the string being to the left, it will be to the right. The process doesn't change. The tension will be going backward, because it has to hold it from going all the way to the right. What happens if you bring in a couple of charges? I'll just show you the picture because I'm not going to draw that. Remember, the positive charge, the field for a positive charge is always what? We're talking about electric field. For a positive charge, always pushing away. Because that means, again, if you bring in a plus charge to this area, what will happen to that plus charge you bring in? They're going to try to push it away. And if it's a negative charge and you try to bring in a plus charge to it, it's going to be pulled in, right? Now what happens if you have a couple of charges next to each other, one positive and one negative? And this is what you're going to see. If you bring a plus charge and negative charge in the neighborhood, this one is pushing away, this one is pulling on it. So this is what you're going to see. The field goes from here to there. Now, if you bring in the charges really close to each other, what happens, you'll see that. That field becomes much, much stronger. If you bring in two positive charges close to each other, they're both pushing away. This is what's going to happen. So the area in the middle right here, notice has no field on it. Because they're pushing away. They start to drift away from each other. So you just got to be aware of it, like what's happening there. Which spot, hopefully the charge is like this, but if you're talking about right between them, if you draw a line between them, this spot looks like dead spot. There's nothing in it. Because this one pushing away and this is pushing away and equal. If these charges are equal amount, the result's going to be zero because they're going to cancel each other out. And again, this is what the capacitor, the charge for the capacitor looks like. The field is always going from here to there. There's an equation to calculate the field based on the area, based on the charge, based on the distance between them. The farther the distance, the weaker the field. The closer the distance, the stronger the field. The more charge that you put there, the stronger the field. The less charge that you put, the weaker the field. What is between them? Is it air? Is it glass? Is it metal? Is it water? Is it rubber? That will determine the value of either. There's a lot of factors that will determine that. There's a whole science in them. I talked about the Science Museum in Boston. This is the experiment they do. They have somebody inside that cage, and you see the lightning, you hear the lightning, and that person is actually touching the metal. And people go like, why isn't he getting zapped? Again, the reason, the charge always, you're putting that charge, and that charge wants, same charge, they want to be as far as possible from each other. And the way you charge this, by the way, a positive charge, they take a negative rod to this. Well, when you take a negative rod, the plus charge is going to come to this end, leaves that end to being negative. If you take a wire and attach it to the ground, these negative charges will go to the ground. These still attract to this. Now you move the wand away. Once you move the wand far away, this becomes a plus charges here. Well, they don't like each other. They're going to spread as far as possible from each other. And it goes on the outside of that shell. So that's how we charge something positively or negatively. We can do that in the lab. I mean, the only thing you feel, we have a little styrofoam, you can touch it and you see that becomes a plus charge or negative charge, you know? Or sometimes you take a young lady, a young girl with like really light hair, and we used to have a generator there, but somebody didn't like it, chopped the wire. She was afraid it's going to zap somebody, cut the cord to it. And it's a belt actually that goes around. When that belt goes around, frees these electrons. We had them put their hands on it, and you'll see that charge goes to their hair. And because they're all negative charges, they want to be as far away as possible. So you see the hair goes like this, stands up in the air. And it will stay like this for a while till the person takes their shoe off and step on the ground. Once you take your shoe off and you step on the ground, you have a path through your body for that charge to go to the ground, and the charges will disappear. But if they leave their flip-flop on, they can be walking with hair looks like crazy there. That's where the charge is on it. This is actually a good, interesting question. Well, maybe this one. Let me take this problem here. Where's electric field? Here we go. Okay. We'll do this example. I have an object with a charge of negative 3.6 microcoulomb. So I have an object here, and I don't know anything about this problem because I really didn't read it. I just see one here. Has a negative charge. So the charge for this is negative 3.6 microcoulomb. This object has a mass of 0.012 kilogram. Experience an upward field, electric force. There's a field here. That's why the object. So for some reason now there's a force pushing upward on it. And that force pushing upward due to uniform electric field equal in magnitude to the weight. That force is equal to the weight. Well, if you think about this, the fact that electric field or the force is pushing upward, that tells me I had a field here. And which way? The negative charges must be on this end, and the positive charges must be on that end. Negative to positive, I'm putting a negative charge. This negative is going to be pushing on this upward, this is going to be pulling upward. That's why the net result is a force pointing upward. If it was pushing down, that means the plus was on this end, the negative was on that end. So I know which way it actually was. And so there's a field right here, and the field always goes from plus to minus in a plate. Again, the field is based on if you put a plus charge, which way the plus charge will go in that direction. The fact I'm putting a negative charge is going to move backward. Find the direction of the magnitude of the electric field. If the electric charges object is doubled, if we make the electric charges doubled, and its mass remains the same, find the direction magnitude of the acceleration. Okay. We'll deal with that after. We know the direction of the field has to go down. Okay. Why isn't the object is moving? Because we have, there's the charge here, we have the weight down, we have the mass, which is 0.012 times 9.8, 0.1176. We have a force pushing upward, and the value of that force, the magnitude of that, is Q times the electric field. Q for this is what? 3.6 micro. Again, the sign just tells me the direction. And it says in the problem that this force has a value equals to the weight. If it's equals to the weight, that means Q times E is going to equal M times G. This force has to equal to this. 3.6 micro times E equals the mass, or the whole thing is 0.1176. Can we get what the electric field is? Divided by 3.6 micro. 32,667 Newton per Coulomb. That's the first part. Now there's part B to it. We know it's pointing down, the direction of it. Part B now, and in part B here, if the electric charge, the object is doubled, so the charge now, it's no longer negative 3.6, it's negative 7.2 microcoulomb. And the mass remains the same. Find the direction magnitude of the acceleration. Well, we know this is going to, that's a negative charge, so it's going to go upward. The direction is going to be upward. So the force here, which equals Q times the electric field, it's pointing upward. The weight is down, And they are not equal to each other. They're not. So we have this one, Q, which is what? 7.2 micro, times the electric field, which is, I have my electric field from 2 minutes ago to be 32,667. That's the force upward. The force down, we know that's the weight. And I have that number to be what? 0.1176. What's the top number? 7.2 times 32,667. Notice this force is larger than that. Newton's second law says what? The net force equals mass times acceleration. The net force equals the mass times the acceleration. Well, this force is larger than this. So my net force is going to be 0.236 minus 0.1176 equals the mass of the object, 0.012, times the acceleration. Can we get that acceleration? I'm carrying all the digits for this one, so my number might be a little bit different than yours. My acceleration, guess what? It's 9.80 meters per second squared, upward, equal to gravity. Make sense? Electric field versus forces. Electric field, me putting a charge here and walking away from it. That charge radiates. It's either going to create a field pushing away from it or a field going to it. Pushing away if it's a positive charge, going to it if it's a negative charge. And nothing will happen till I bring in a charge to the neighborhood. Once I bring in this charge with me, what is this going to do to that one? It depends, because if that's a plus charge, this will push it away. If that's a negative charge, it will suck it in. And the value of that force will be whatever that charge times the field. Forces are different. Forces, you have two charges there. It could be one negative, one positive. If one is negative, one positive, they're going to pull on each other. And if they are free to move, both will move toward each other. Opposite attract. If they're the same charges, they repel, they go away from each other. And the value of the force, we showed you how to calculate the value of that. So that's the difference between them. Capacitors, you saw that. Those are popular actually in electronic device. I'll bring some and show you what they look like physically.